We want to show in this problem that for two convex sets, their intersection is convex. First, let's note that if A and B are convex, we know that for any A and B, let's call them A1 and A2 in A implies that alpha A1 plus 1 minus alpha A2 is in set A for any alpha between 0 and 1. Similarly for set B, B1 and B2 in set B tells us that alpha B1 plus 1 minus alpha B2 is in B for any alpha. Okay. Now, in the event that A and B have nothing in common, so if A and B, A and B is empty, then A intersect B is convex. And it's convex in this case because for any C1 and C2 in that intersection, there is no value of alpha for which alpha C1 plus alpha C2 is not in that intersection. Okay, so this is by definition, in a sense. Now, let's suppose that that intersection is not empty. If A intersect B is not empty, then there exists at least a C1 and possibly a C2 in A intersect B. Okay. If I'll talk about the situation in which you only have a single point in a second. So let's assume there's at least 2 points in that intersection. Since C1 and C2 are in the intersection, C1 and C2 are in A, and C1 and C2 are in B. Since they're in A and B, alpha C1 plus 1 minus alpha C2 is in A, and alpha C1 plus 1 minus alpha C2 is in B for every alpha. Because that's the definition of what it means to be in sets A and B, given that they're convex. Okay. But then we're done. So therefore, alpha C1 plus 1 minus alpha C2 has to be in A intersect B because that's a point in A and it's a point in B. So A intersect B is convex with greater or equal to 2 points. If A intersect B is equal to a single point C, then A intersect B is convex by definition again. Because alpha times c plus 1 minus alpha times c is equal to c. And so we're done. We dealt with the case where A intersects B is empty. We dealt with the case where A intersects B is a single point. And anytime we've got two or more points, we've shown that the line that attaches those 2 points is also in that intersection. So we're done.